So thank you for having me on the seminar series again. Let me start with introducing myself a little bit. I'm a professor at ECE. I have joint appointments in CES and Creole. My PhD is from RPI 2002. And my research interests are in computer networking in general. More recent focus I have is in wireless systems, optical wireless specifically. I also have work going on in spectrum sharing, cloud networking, network economics and architectures. Those are sort of like traditional work that I have been doing, as those were my PhD topics. Today, mostly I'm going to talk about wireless and specifically optical wireless. And I teach in systems and networking areas. 3 courses I've been teaching at UCF have been communication networks course at the senior level, which is a required course for computer engineering and elective for EE. And network economics and architectures is a 6,000 level course I'm offering, and software-defined networking is a 5,000 level course I'm offering. I direct the networking and wireless systems lab, and I graduated. I mean, essentially, we look at experimental and theoretical aspects of various computer networking and communications issues. And then essentially, we are trying to mostly focus on what is needed out there, and also trying to keep ourselves in the fundamentals as much as we can. I graduated 15 PhDs so far and 2 postdocs, and I've been able to, fortunate enough to collaborate with many great people so far from various institutions as well as industry. My sponsors have been mostly NSF, and then I do I did have some funding from DoD and NIST, as well as some funding from industry. As I said, I'm going to mostly focus on wireless in my talk today. I just want to give some recent numbers on where my work positions itself. In terms of the wireless, in terms of the overall internet growth or the growth of the internet traffic, in the recent years, according to Cisco report, which is the golden standard in terms of these statistics, most of the growth has been in the smartphones. And as you can see, about 5 years ago, smartphones were occupying about 23% of the overall internet traffic. Now they are occupying 50%. Of course, we will still have PCs and several other things, but the mobiles are now dominating the internet traffic, which is clearly forcing ourselves to think about what to do. Another important number I would like to get your attention to is the number of devices per person has increased, almost doubled in the last 5 years. So these are important trends and certainly pushed the wireless community to look for solutions in terms of what to do with the capacity scarcity. That's where it boils down to. Traditionally, wireless community has been using this particular band I just highlighted, which is, essentially most of the wireless technology we have is using cellular and Wi-Fi, and they are mostly narrowed down to this particular band of frequencies in the electromagnetic spectrum, which use centimeters to meters in terms of the wavelength. These bands have very nice features, which I'll talk about quickly a little bit, but the problem is that it doesn't have enough bandwidth anymore. It just is too much saturated. So recently what happened is that the wireless community started looking at these higher frequency bands at the millimeter wave and free space optical or optical wireless, or more generic term is actually terahertz communications. Again, all of these are considered in the context of wireless. I'd like to get your attention to the fundamental change in this. Legacy systems, legacy wireless systems have been using omnidirectional radios. They're great for handling mobility, but they just, as I showed, they just don't have enough bandwidth. And in terms of the overall 3 goals we have in wireless system design, which are rate, mobility, and range, as I'd like to call, mobility was the main thing to start with, and then the designs were sort of like trying to increase rate and range. With these higher frequency bands, what we have is another way of looking at these trade-offs. We now have rate. These bands, as I showed, has lots of bandwidth. I mean, these frequencies have lots of bandwidth, millimeter wave, FSO, and terahertz. But the problem with them is that when we realize them in reality, they end up becoming very directional, which means that they are very handicapped in terms of handling mobility, because you have to have essentially both the transmitter and the receiver looking at each other, which is the problem of line of sight and line of sight alignment. Traditional approach to solving this have been using lasers or expensive devices, long-range point-to-point links. DARPA, for example, funded for decades very sensitive mechanical systems that were essentially trying to align in the order of micrometers movements. A large mechanical system on the ground looking towards a UAV, sending a very high-powered laser signal with lots of data in it, of course, from a UAV. My approach in my group is, rather than doing these type of long-range point-to-point links, let's focus on multi-element modules, and inexpensive components, optoelectronic components, like LEDs, cheap lasers, which are called VCSELs, and use a redundancy of them, and use them on surfaces that are angularly diverse, like spherical surfaces, and to handle mobility with the help of some electronics. Let me show what I mean. First of all, let me make sure that it's understood. FSO, I will keep referring to it, means free space optical. Another way of looking at it is essentially fiber optic signal without a fiber. Sometimes we just also call it optical wireless. So the key aspect that we have been looking at for more than a decade, actually, in my group, is merging angular diversity of spherical shapes with these highly directional transceivers or FSO transceivers. If we merge them together, we get actually nice availability of line of sight. Even if you have these two such modules, FSO modules, multi-element FSO modules, moving with respect to each other, there will still be a transceiver on them that will be aligned with each other. The problem, though, is that instead of mechanically turning them, like DARPA funded for years, we can select which transceiver to use on the fly by using some protocol, by using some autonomous distributed on-the-fly protocol. So we showed this concept in various projects, prototyped it, published several papers, related to how exactly this can be done by merging all these three main things: directionality, angular diversity, and electronic steering. In terms of these modules, there's still lots of work to be done. Currently, this is an SBIR phase 2 project that I'm doing. I mean, on this particular direction, I have an SBIR phase 2 with Triton systems. Lots of things that need to be done, both involve hardware and software. How to miniaturize these type of systems, these type of modules. How can you integrate them to airborne platforms? Lots of very interesting problems to be solved. Another thing another area related is multi-element VLC. I'm just going to try to quickly go over them. Optical wireless work that I showed in the previous two slides is mostly using infrared, not invisible optical bands. A very nice application of multi-element optical wireless modules is usage of LEDs. And we already have lighting systems, and our lighting systems are moving already towards LEDs. And specifically, the concept that I'm exploring in this space is, how do we take bulbs that may be using only one LED? This has been the typical approach to VLC, by the way, I forgot to mention. VLC means visual light communication, or visible light communication. The idea is essentially to send both data as well as light to an indoor room. Instead of having a Wi-Fi access point, or in addition to having a Wi-Fi access point, send the data through the light as well. So that's that key idea of VLC. It's not a new idea, but traditionally this has been tackled by a single data stream, which means you have a LED which sends the signal to everywhere within the room. But the problem with that is that if you have multiple receivers in the same room, they cannot use the space. If you have multiple LEDs on the bulb, you can actually send data to each one of these receivers at the same time and achieve what we call as spatial reuse in communications. This idea has lots of issues, and which we tackled in various projects so far. How do you design VLC receivers for mobile platforms? By introducing multiple LEDs on the bulb, you're introducing the problem of lighting uniformity, meaning that the light needs to be now, obviously you want the lighting to be as uniform, as smooth as possible in the room, but with multiple LEDs, now you have the problem of spotty lighting. And also, if you have got multiple LEDs, how do you associate each LED on the bulb to individual receivers? These are some of the major problems with this idea. We tackled each one of them. For the sake of time, I'm going to skip them quickly. In this one, for example, we prototyped a VLC receiver that has a large area, which is like, this is considered large, by the way. I mean, when we say a receiver, you can consider your smartphone's camera is a receiver. It's a photo detector. If you look at it carefully, it has a millimeter square surface area. Like in terms of the reception area, it has a very small area. There's a reason for it, because if you increase the size of the reception area, the effective bandwidth reduces on these receiver systems. We showed that we can increase the reception area, the large surface area of the receiver, to centimeter squares, which is a big leap, while still keeping the overall bandwidth at 20 megahertz. This was the key contribution of this work. Another area that we looked at, lots of optimization problems arise here, is how do we handle the issue of many mobiles? If I've got many mobiles in the room, again, how do I keep the association of each LED on the bulb to individual receivers? We looked at several optimization problems. How, this association problem is one thing. What you're seeing is actually, just recently we looked at the problem of what if we put mirrors on the walls? These are the kinds of shapes that you end up getting in terms of optimizing both the communication as well as the lighting efficiency in the room. Recently with Creole, we just designed another system here. We have an LED array behind a lens system. And the lens system actually is designed in such a way that each LED corresponds to a particular spot on the room. So it's hard-coded in some sense, which LED is supposed to be looking at where. And that actually helps in terms of how to figure out which one of these receivers are located and which one of the LEDs are supposed to be used for those receivers. So the association problem actually is simplified. So we showed how exactly this design can be tuned by placing this LED array to the focal point or defocusing it, because you do have, as you can see, you have a spotty lighting, and that's where you get the maximum throughput, maximum communication efficiency. But as you defocus it a little bit, you can get better lighting, but of course that impacts your communication efficiency. We looked at the trade-off involved in that. Let me skip this for the sake of time. Those were the optical wireless work. There's an ongoing work that we have. I'm leading an NSF project on directional software-defined radio. From both my collaborators are from ECE, and in this one, we are looking at similar concepts, multi-sector antennas. As you can see, each one of the sectors is going to be essentially having a phased array millimeter wave antenna, which essentially can steer the beam on the fly. And in this one, though, we are using millimeter waves. We are not using FSO. And we are looking at, again, very similar problems. Recently, we are looking at the problem of how do we assign, given these directional radios, how do we make coalitions of them, which is a very fundamental problem to be solved. Another recent NSF project that just started in fall semester is, I'm the single PI on this one. This is essentially looking at the problem of how do we make drones use optical wireless or directional, not just optical wireless, but I'm going to use optical wireless as part of this project. How do we make drones use directional links to establish a sort of like an airborne backbone network? I call it 3D directional mesh network. This idea is not entirely new. Actually, Facebook tried some of it, but at very high altitudes. I mean, I think that the name of the project was called Aquila. I'm hoping I'm pronouncing it right. But essentially what they were doing is they were planning to put very high-flying UAVs, and then the goal was to provide connectivity to rural areas of the world. Google actually has been doing this balloon-based idea, again, very similar. In both of those projects, they aim to use very high-end lasers in order to connect balloons for the case of Google, and in the case of Facebook, again, they were trying to interconnect the, I think they were glider they were using for implementing UAVs. So this is a new concept we are exploring. We have been following up on this idea. We did have several experiments with the UAVs we have done at UCF. But the overall idea here with this NSF project is to realize these inter-UAV laser links. To wrap up, I do have a few other projects that I'm right now running. And as I said, I have several other than the optical wireless, I have several other work that are going on. One of the NSF projects that I'm involved in and participating in is having ISPs, internet service providers, collaborate more by facilitating better peering. So just to quickly, the idea there is that ISPs have to peer with each other, co-work with each other, collaborate with each other in order to provide end-to-end connectivity. In this project, we are essentially trying to make that easier by using concepts in game theory as well as in what I call it as meta-peering tool in this project. There are two other projects that I have been doing. One of them is how to use internet's congestion control mechanisms to integrate electrical vehicles into the power grid. We have published some very nice papers from that work. This has been actually in collaboration with Alabama as well as now NREL. And then another work that evolved was spectrum sharing. Essentially, I led this project. This was an NSF project. We wrapped it up last year. This involved essentially how very similar ideas to the peering, but in the case of wireless though. The idea there is that if we can make wireless operators, as you may know, they actually compete fiercely to get a chunk of the band, wireless band or the spectrum. So what if the sharing was the norm is the key idea, the key question we asked in that project. Thank you for your attention.